conference. Yeah, so today I will introduce you the equilibrium landscape of the Heisenberg spin chain. So what I have in mind by that is the complete space, the complete manifold of all local equilibrium state that you can construct in this model, which I'm pretty sure you all are very familiar with. So this is work in collaboration with Owen Quinn. So I didn't really intend to spend much time on the introduction, since especially after Marcos made a wonderful job in covering most of the important aspects of it yesterday and today. So I probably don't have to convince you why the subject of thermalization in closed many-body quantum systems is worth studying, and why it involves many interesting theoretical aspects. So here I listed a few of them. So one could study the phasing mechanisms, then the eigenstate thermalization hypothesis, which Marcos explained. Then I forgot to mention entanglement, obviously. Then one could study relaxation of local observables, and equally focusing on large times, where one can develop various hydrodynamic approaches to that. There were already talks about it, and more are coming this and next week. But what I would like to really re-emphasize is that integrable systems, such as the Heisenberg spin chain, which I'll be addressing today, are very special in this respect because of the extensively many local conservation laws that they possess. And as Marcos already explained to you, then the conventional paradigm of statistical physics breaks down in the sense that canonical Gibbs ensembles are no longer states which describe equilibrium states in such systems, and one has to appropriately generalize them to what is known today as the generalized Gibbs ensemble. My main point of today's talk will probably be that interacting integrable systems are much richer than their non-interacting cousins. Namely, they exhibit really features that go beyond what you can find in non-interacting models. And I will want to explicitly demonstrate this fact today by giving you an explicit construction of this equilibrium landscape. So the problem I'll be addressing is basically find an explicit construction together with the complete characterization for all the admissible local equilibrium states which you can find in this model. So the isotropic Heisenberg spin chain. Okay, and without further ado, we have to delve into integrability. So, so I hope that most of you, yeah, sure. Not in particular, but it has a bit nicer structure, especially because if I take the anisotropy in the gapless phase, then I start to suffer. So I wanted to just take the simplest possible model to address this question first, but obviously it can be generalized to anisotropic. There is no obstacles really. Yeah. So, so I have to start with the so-called Lax operator, because this is the most fundamental object of quantum integrability. It's an operator that lives in two spaces, and these are both some representation of SU2 spin. So one representation is the fundamental, which I denote by 1. Because my spin chain, my degrees of freedom live in the fundamental representation, and the other is just a generic finite dimensional representation for spin. And then I construct an object like that. So it's just the tensor product of spin generators, sum over all generators, and it has this trivial dependence on two complex parameters V and U. So why is this object important? Well, first of all, I can use this object, make a tensor product, so I can create a spatially ordered product like that. And if I'm tracing out this k+1 dimensional spin representation, I will end up with some object which is known as the transfer matrix, which has this nice property that it commutes for all different values of k and all different v's. So I just constructed an abelian set of commuting operators, right? So. And this means that I already have infinitely many conservation laws, in particular because V is a continuous parameter, and well, K is a discrete parameter. So I have two labels to label my conservation laws. Now, these transfer matrices themselves are non-local, so don't have really any physical meaning a priori, but one can use them to construct the local conservation laws, which will be the key objects in constructing the local equilibrium ensembles. And this is achieved in the following way. So you take this general transfer matrix that I constructed this way, and you basically take the logarithmic derivative with respect to this vector parameter V. And you end up with some objects, some operators, which I denote by x, k, v. So it's, now these are still conserved manifestly, but I claim that they are local, provided this spectral parameter v resides in some region in the complex plane, in some strip in the complex plane, which is of width 1, okay? So its upper bound is I over 2, and its lower bound is minus I over 2. Now here I put some epsilon. So this epsilon is, as usual in mathematics, positive infinitesimal, which is just there to prevent me to hit the boundary of this strip. This may seem like an unnecessary detail, I'm telling you now, but it turns out that this whole business that I will be explaining you in a moment is crucially relies on the presence of this epsilon, and if you don't take it properly into account, absolutely everything goes to waste. So the physics is kind of very important. It's related also to locality. Yeah? So you see it for this definition. If you don't put this epsilon, then you hit the boundary of the strip and you sort of lose locality of these objects. So this family of operators, this two-parametric family, includes both the local conservation laws and what is known as the quasi-local conservation laws, which is a slightly generalized notion of locality. But for these purposes, quasi-local conservation laws should be treated on equal footing as the local ones. And today I will not really dig further into that. So if you like to know more about this distinction, you can catch me at the talk. I'll be happy to explain you more details. This, yeah.
You say you don't.
Correct.
Is that what is?
Absolutely. So this object, if you expand it in a Pauli basis, for instance, you will find that unlike for the local charges where all the densities are compactly supported, these guys don't have compactly supported densities. They have localized, exponentially localized tails in particular. It's just that. Thank you for this. It's just that. So, and then I'll be using also this notation, plus minus. If it appears in the subscript, it means that I'm shifting the spectral parameter by this imaginary unit up or down. And in case if you wonder where is the Hamiltonian hidden in this family, it's just if you take the fundamental spin representation 1 and put v to 0, then basically I recover the Hamiltonian. Okay, so you will see in a minute why this is important to define it this way. Okay, so first, maybe very quickly, why are these local and quasi-local conservation laws important? So this goes back a few years back where we tried to understand whether interacting integrable models are thermalizing, and in particular, if they are thermalizing into a generalized Gibbs ensemble. So the setting is like this. You consider some pure initial state, evolve it unitarily under your Hamiltonian, and then you evolve it for a long time, and you look at some expectation value of local observable, right? The question is this expectation value equal to the trace of this observable with respect to some steady state ensemble, which has the GGE form. And there was a lot of work on that, yes, no, and then in the end, the answer to the question turns out that, that indeed this is possible, provided you are able to identify and include all the local and quasi-local conservation laws in the game. So the algorithm to solve this problem basically goes as follows. So you have to find some convenient explicit representation for these charges. I just gave it to you. Then you just take the initial state, you compute the initial expectation values. Okay, you have to find again some method which allows you to do that. And then the tricky part is this. So you basically, once you have these values, you have to be able to transform these expectation values into the quasi-particle rapidity densities of this model via a particular relation. So I will tell you more about this relation in a few slides. This is called the string charge duality. So once you're able to map this information into information contained in the quasi-particle distributions, then once you have express the local observables as appropriate functionals of these quasi-particle distributions, you are able to basically compute the expectation value for local observables after a quench. Okay, so this was the story. This goes, I think, 2-3 years go back, and the question at this point arises, okay, so that's it. So we know that the idea works. We found an example. So is this the end of the story? Is this all that one can say about thermalization? And I want to convince you that the story goes a bit deeper. And in particular, there are the following idea, or the following objective I had in mind when I delved into this. So first, the natural question to ask is, what is the most transparent and efficient way for representing a general Gibbs ensemble, so the reduced density of a general Gibbs ensemble? And in particular, how to construct an explicit representation of it, which also allows you to systematically approximate it. Okay. It turns out that to solve the quench problem, you don't really have to go into that. You can kind of avoid this problem. And after you do that, of course, the question is, what is the complete characterization of all of the complete sets of the whole manifold of local equilibrium state, the so-called landscape, right? And now I will outline basically two approaches to thermodynamics with which I can address this question and solve this problem. And these two are basically, these two approaches can be viewed as complementary approaches to thermodynamics. One is just the functional integral approach, which is better known as the thermodynamic Bethe Ansatz, which crucially relies on the knowledge of exact eigenstates and their quasi-particle structure. And the other is also another traditional approach of StatMech, which is the transfer matrix approach, where one has to construct a suitable two-dimensional classical vertex model and compute the associated partition function. So it's always possible, to remind you, it's always possible to represent a partition function of a one-dimensional quantum system as a partition function of a two-dimensional classical system. And this is what I will show you later, okay? And so the objective is now to carry out all these procedures to the very end and then establish explicit equivalence between the two, okay? So we know on the physical grounds that these two approaches must be the same, but it's interesting that, at least to my knowledge, this has never been achieved explicitly in any paper, despite integrability is probably a 100-year-old discipline. Not even in the context of classical vertex models, which go back to Baxter and others. So in this respect, I think this is basically the first explicit complete solution of equilibrium in a many-body interacting system. Okay, so quickly about basic notions of integrability. So Lax operator not only allows you to construct the entire family of local conservation laws, but also permits algebraic diagonalization, since it basically allows you to define a quasi-particle creation operator. So it works like this. So you start with a trivial eigenstate, which is just the ferromagnetic vacuum. And then you constrain the whole spectrum of eigenstates by basically generating magnon excitations on top of this state. And you do this by applying sequentially this B operator, so the creation operator. Every time you apply it, you create a magnon which carries rapidity ui. So this ui is a parameter that each magnon carries. And rapidity is just something that parameterizes magnon momenta via this relation. Okay, so I'll do that. I apply it m times, and I will create a many-body state with m magnons, which I denote like this. The non-triviality enters due to the fact that magnons are not free, they are interacting, which means that these numbers are not at all free. Okay, they are constrained. So what is happening? So imagine the magnon you had just one magnon propagating in a system with periodic boundary condition. Then the only restriction to this rapidity would be that the quantization condition due to periodicity. So e to the ikl equal 1, as in free fermions, right? But now imagine there is more magnons, so magnons non-trivially scatter. You have to basically appropriately generalize this condition. Of course, there is no reason why there should be some trivial relation, but the miracle of integrability is that the whole many-body scattering process of magnons completely factorizes down to a sequence of two-body processes only. Okay, so integrability is really a two-body property. And the two-body scattering process of magnons is completely encoded in object S, which you call the scattering amplitude, and it's this simple rational function of u. You can think of the difference of the rapidities of incident magnons. So what you have to do every time two magnons scatter, you just put this scattering amplitude, and then this is your generalized quantization condition, better known as the Bethe equations, of course. Many of you probably know. Okay, so the next thing is that in this model, magnons is not the end of the story. It turns out that interaction is attractive, so magnons can form into bound states. So bound states, basically, you detect bound states by the presence of complex rapidities. Whenever you have complex rapidities, it means you have some decay in the magnon wave function, which tells you that this magnon is a part of some localized state. So basically, what you have to do, you have to repartition the whole set of original magnons into sets of magnons which belong to one bound state. Okay, this is just repartitioning of the whole set of quantum numbers. So now, bound state of magnons scatter with other bound state of magnons. So you have to find the generalized scattering amplitudes. This you just obtain by fusing the constituent magnon amplitudes. And then you get to the equations which are known as string Bethe equations. Why strings? Because these magnons, which contain bound magnons which contain J constituent magnons, are called J strings because because the way you see this, the corresponding rapidities really form string-like patterns in the complex plane. So this is where the name comes from. Okay, so now instead of original magnons, my quasi-particles are these strings. And these are the quantization equation for them. Why is this nice? Because it's nice, it's easy to go to the thermodynamic limit. You just make the system size large, and all the numbers of magnons of type J go also is large, such that all the ratios are kept fixed, right? And now what you do, when you have a big system, there will be exponentially many magnons in each eigenstate, and the rapidities of these magnons will start to approach each other as 1 over system size. So it means that once you are in the thermodynamic limit, you can switch from discrete summation to integration over densities of magnons. So now we introduce as thermodynamic variables these densities of magnons and also the corresponding densities of holes. These are just the density of vacancies of magnons, if you like. And this allows you to transform these equations into some coupled integral equations of this type. So some convolution type integral equations for all the densities of magnons and their holes. These are known as the Bethe-Young equations, and the kernel of this transformation, so star here is just the ordinary convolution. The kernel is directly related to the scattering amplitudes, which I defined before. Why is this important? Because now for the thermodynamic states, you basically, you don't think in terms of individual particles, but their densities. And now solutions to these Bethe-Young equations are basically given in terms of sets of densities of quasi-particles, and each set of such densities defines a unique macro state of the model. Macro state or a microcanonical sample, if you want, okay? So this is a collection, unbiased collection of many, exponentially many microscopic configurations, eigenstates, which are all locally indistinguishable. So if you measure local correlation functions, they will all give you the same value. And then all you have to do is have to know how many of these configurations belong to one macro state, and this number is given by entropy, which is spelled out here. Okay, this is the approach that Yang and Yang developed in the '69, and as you probably noticed, this is basically nothing but the eigenstate thermalization hypothesis adapted to integrable system. Okay, this reduction from microstates to macrostates. Okay, now I think I'll have to tell you a bunch of technical stuff, which I will need later, so I'll try to go very quickly through that. So don't worry if you don't catch all the details, because it's maybe rather cryptic. The point is that with this formalism, there is a bunch of operations that play a very important role and allows you to basically identify the algebraic structure underneath. And there are some caveats along the way, and these caveats play a crucial role at the end of the story. So in particular, it's about this. So this Fredholm operator, which appears in this Bethe-Young equation, is an operator that admits an inverse, but it only admits the left inverse, not the right inverse. So it's not invertible. So if you express the left inverse in the standard way via the Fredholm resolvent, it will have the following structure. So it's a product of some matrix, which you call the incident matrix, and some function of rapidity. So let's call it just the S kernel. And now both this 1 minus R operation and the S kernels have non-trivial null spaces. This means in particular that if I take some general function f, then I convolve it with this S, and then I deconvolve it or apply this S inverse, I will always get the same function back. But if I do it the other way around, if I first deconvolve it and then convolve it, I will not always get this function back. Okay? It will be clear in the next slide why this is important. So moreover, this operation S inverse I can conveniently represent by simply analytically continue from the real line to the complex plane by this unit imaginary shift. And again, here I have to be careful when I do this analytic continuation. I have to force this epsilon prescription over there. So I mentioned this object has a null space, and one can identify what are the functions that span this null space, and they have this form. So these functions are denoted by tau, and are parameterized by some number W, which has to live inside this locality strip. So the strip where the charges have the locality property. The next object I need to introduce is the discrete D'Alembertian, which is, again, related to this pseudo-inverse in the following way, and has the following action on this function. So it's shifting the complex plane and then shifting this to indices. So it's really like a discrete version of the wave operator that you're familiar with. And then once I have this D'Alembertian, I can ask what's the green function for it. So the function that satisfies this condition, and I can identify it is this function. And this green function I can moreover express in terms of some amplitudes phi, psi, what is this, psi, which again I can explicitly express in terms of magnonic scattering amplitudes. And also this D'Alembertian operator is an object which is non-invertible. It has a non-trivial null space, and the functions which are inside this null space are basically inherited from the null space of the S inverse via this prescription. And the last thing, technical thing that we need, so now I'm basically just laying down all the key ingredients that I need in order to solve the problem. So first is the thermodynamic inversion identity, which is basically telling you that if you take the product of these transfer matrices that I initially introduced, appropriately shifted and normalized, this will give you 1. This is important because in the definition of the local charges, we had the logarithm, and with this identity, you're able to get rid of the logarithm in the thermodynamic limit, and then you are in business. Otherwise, whenever you have logarithm, you suffer. Huh? The other thing is the so-called string charge duality, which I mentioned before, which was the key ingredient to solve the quantum quench problem. And it means the following. So if I give you the expectation values of these local and quasi-local conservation laws, I can always relate them to the values of these Magnon's distributions and their bound state. And the relation is if you have distributions, you basically just convolve them with this green function, and voila, you have your expectation values of local charges. And not only that, this equation can be inverted, so you can express the quasi-particle densities once you know the charges by simply acting with the D'Alembertian on it. And since the charges, so the eigenvalues of the charges belong to a commuting set of objects, there is no problem of lifting this equation also on the operatorial level, okay? And this was very important, okay? So now, once I have this, I can write you down most general form of the generalized-Gibbs ensemble in this model. So this is the way I will write it, and you probably recognize already this is not the conventional way of writing GGE. So what I will use instead of the conservation laws, local conservation laws, I will use directly these mode density operators that I obtained on the previous slide. So these basically inherit locality from the charges X, so these are well-behaved objects. And then the associated Lagrange multipliers, or chemical potentials, are these functions mu. And then I have to add, obviously, the conserved magnetization, which because of the SU2 symmetry, and I have to add all 3 components of it. Okay, so this is some what I call Cartan charge. And there is some technical extra requirement, which is not so important at the moment. So the question is, why is this better than this conventional way of writing as a discrete sum over some basis of charges? Well, I can give you 2 reasons. So first, this definition is even ambiguous because when you have this sum, it's hard to make mathematically sense of it if this sum is infinite. It's not clear in what sense this would converge. If, of course, you can truncate it, then it's okay, but then you make some approximation whenever you truncate it. And the other problem is that here there is ambiguity of which basis of charges to use, because what you find in the textbook, for instance, is just one basis of charges, but these charges form a linear space of operators. You can always introduce another basis, and then this beta, the Lagrange multipliers, will change. And then you can start asking, okay, but is there then any physical meaning of these betas and so forth? So this definition, in contrast, I argue clearly conveys the physical picture which sits underneath the GGE concept, since these mode density operators, if I look at their spectrum, will give me precisely the density functions for the quasi-particles for that particular macro state that this ensemble corresponds to. And moreover, this notation, this is gauge invariant object, so it doesn't suffer from normalization, ambiguity, and so forth. Okay, so I promise you two approaches to the thermodynamics. So the first one is just the TBA approach. So what you do, you cast the free energy density in the form of a functional integral, where your variational variables are already these quasi-particle densities that determine macro states. You demand that variation derivative vanishes, and you find some couple set of integral equations, which you conveniently write for the functions which you call the thermodynamic Y functions. These are ratios of the holes and particle densities. So in terms of these variables, you have a nice set of equations like this. And what is nice is that the source term of these equations, which is where the state dependence enters, the source term is nothing but these analytic chemical potentials that we defined. You can do even more. You can simplify that by convolving with 1 minus r, and you will find a form where on this side you will have only the neighboring thermodynamic Y functions of this one, and the source term will transform accordingly. And finally, to have a unique solution of this equation, you always must demand the correct large J asymptotics, which is where dependence on this unique chemical potential associated to magnetization is hiding. So this is just one possible way of representing the thermodynamic Bethe Ansatz equation. There is another way, which instead of using a coupled integral equation, is using functional relations for complex valued functions. So the idea is to just simply analytically continue these equations into the complex plane, and then you can close them in the following way. So you see this plus is just a shift by one unit in the imaginary direction up. This is going down. Again, I must be careful with this epsilon prescription, and I will find this kind of equation, which I call the thermodynamic Y-system. So those of you who are familiar with with the Y-system will immediately notice that the presence of this term over here is weird, because if you open the textbook, this term is not there. Moreover, the textbook will claim you that this is the universal equation which is underneath all the integrable models which have the same symmetry as Heisenberg spin chain. So this really should follow for some group theoretical reason, but here seemingly I get something else. So why does this term appear over there? It's simply because of this, the presence of this null space of this inverse, so of this pseudo inverse. So it means that these source terms always admit a natural decomposition into one part which resides in the image of this operator, and one resides in the kernel. And the kernel it has a particular structure like that. And the part that is in the image appears explicitly over here, and the part that is in the kernel, you see it doesn't appear explicitly, so you think, it's not present, but it is. It's encoded instead in the zeros and poles of these Y functions, which are meromorphic functions in this locality strip. Okay, so that's basically a technical explanation of the thermodynamic Bethe Ansatz. And the question is now, can one retrieve the same description by starting from a seemingly completely different approach, namely the transfer matrix approach, without resorting to physical magnons, to macro states, and none of that? And let's see how I'm doing with time. Probably not very good. Okay, so the idea is you start again the same expression, this gauge invariant description of a GGE. Instead of the mode density operators, I plug in the charges over here, and then I use this decomposition into the image and null space, which I just explained. And using that, I immediately see that this ensemble factorizes into 3 distinct pieces. And then I will treat one by one. So the first piece is the node data, because it contains these lambda functions, which appeared in these node terms in the TBA. So what I have to do now, I have to introduce some regularization scheme. I do that simply by taking this lambda function, and I start to sample them with Dirac delta functions. So it's simply, I can sample them in such a way that I can systematically recover this function with a given resolution. So the resolution is just how many delta function I use in this sampling, and I denote by nk. And then I need some additional factor to have a proper normalization. So if I plug in this sampling, we'll see immediately that this part of the GGE basically factorizes into the exponents. And now what I have to use is this thermodynamic inversion identity, which allows me to write any charge as a logarithm of the product of transfer matrices with some appropriate shift and parameters. When I plug this all back, basically I get an expression like this. So the important thing here is that I'm only using product of transfer matrices that I defined on my first or second slide. Okay, I'll show you shortly what this means pictorially. But the same can be done for the other part, which I call the analytic data, because it hides in the analytic properties of the thermodynamic functions. It's a bit more involved calculations, but at the end of the story, using all of what I told you before, you arrive at this expression. So this expression, unfortunately, is not directly a product of transfer matrices, because it's exponent of something times logarithm, and this something can be in general a real number. So if you have this for the given state, then you need to go into the extra procedure of Padé regularization, which I want to skip because it's rather technical. The point being that, let's see, with that is always possible to systematically approximate any ensemble in such a way that all this alpha will be either plus or minus 1. In other words, what is happening here, if I have a function which is non-meromorphic, let's say it has some branch points, I can do Padé approximation in such a way that I systematically approximate it with the meromorphic functions. And once I have a meromorphic function, it will allow me to write this thing again as a product of transfer matrices. So now I combine everything together. I include this term over here, which encodes the Cartan charge. I use theta as the common variable, which include all of these regularization parameters that I introduced along the way. And basically, what I just described you is an object like that. So this is now a two-dimensional vertex model partition function, or just a vertex model, which has a spatial dimension extent L, which is the physical dimension. Vertically is of dimension 2n. This is the total number of discretization parameters that I use. And each vertex in this partition function is just this lax operator with a particularly assigned representation label and parameters, which I call impurity parameters. So, and this is your regularized GGE. And then you can control as much accuracy as you like, how much detail you want to keep in that. So now the objective is to compute the free energy using that object. And here we have two possibilities. One is just the standard way, so taking this transfer matrix, so taking this vertex model, taking trace over the physical Hilbert space, taking the log 1 over system size, taking the limits. This is just the definition of free energy. So this would correspond to iteration of these row transfer matrices in the vertical direction. The problem is that these transfer matrices in the thermodynamic limit, they don't have gapped spectrum. So in order to do that, you will have to use the path integral approach. But this is precisely the TBA approach that I just outlined previously. So basically, this part number 1 is TBA that we already carried out. The other way, however, is to do the following. So instead of defining these row transfer matrices, which I use in the definition of the charges, and iterating upward, I define this column transfer matrix, and I iterate it this way. And the iteration in the horizontal way is a homogeneous iteration, which means I take just the transfer matrix, I take it to the power of L, then I trace over the Hilbert space of this vertical spin chain, and then take these limits, and I also should be able to retrieve the same value of the free energy. And as you can see in the thermodynamic limit, what is happening because of this power L, if this spectrum is gapped, so only the dominant, the leading modulus eigenvalue of this object will win. So you have to basically, you have to identify which is the largest eigenvalue of this object. So the task boils down to this. And this can be done using a functional Bethe Ansatz approach, which basically tells you this, that all the solutions of integrable quantum spin chains appear as particular solutions to this functional relation, this bilinear relation, which is known as the Hirota equation. So in particular, these T functions are just eigenvalues of these column transfer matrices in the present context, and all the state dependence now enters in this source term, which is characterized by functions phi, which contain all the dependence on these impurity parameters that come through the regularization of analytic chemical potentials. So for each choice of chemical potentials, I have this, I assign these parameters, and then I plug this here, and then solutions of these equations will give me the T functions, which is the describing eigenvalues of the whole complete set of spectrum of this column transfer matrix. And then, moreover, you can again do the following. You can introduce some nonlinear transformations of these T functions because they are not gauge invariant, they are gauge covariant objects. So you want to have something that is directly physical. And then you again end up with these Y functions, which I already mentioned previously. But unlike before, these Y functions are now different Y functions. They are Y functions which correspond to this fictitious spin chain which lives in the vertical direction, and they do satisfy the canonical version of the Y-system functional relations, which is like this, without an extra term over here. And once you have these functional relations, you can also transform into equivalent relations on the real rapidity line. There is standard procedure to do that. I will just quote the result. So you can do it for the Y functions. You will have, again, coupled nonlinear integral equations with the source term, which only depends on the locations of zeros and poles of these Y functions. And similarly, for T functions, you have an expression like that, where now the source term consists of two parts. This part over here knows about the regularized chemical potentials, as I just mentioned, and there is an extra part which explicitly depends on the locations of zeros of these T functions. So here is a problem, because if you want to determine these zeros, you will have to solve some equations which are essentially Bethe-like equations, some quantization equations, and there is no hope that you can do that analytically. So it looks like you got stuck at this point because you cannot classify the whole spectrum of these column transfer matrices. However, I remind you that we are not interested in the whole spectrum, but just at the dominant eigenvalue. It is only the dominant eigenvalue that knows about the equilibrium free energy of the original generalized Gibbs ensemble. And this is a distinguished eigenvalue which doesn't need these parameters. Okay, so I will have to conclude. So basically, what is happening, okay, this is an important example. So somewhere in the middle of this procedure of regularization, a typical Y function of this column transfer matrix has the following structure. So it has some zeros and poles inside this locality strip. And then it has a lot of zeros and poles which start to condense at the boundary of this strip. And then the larger resolution I use, the closer they go to this boundary. And then in addition, if I had originally some branch points, I would have to dissolve them into a sequence of zeros and poles, which will then appear as vertical condensates like that. So that's your typical picture. And the final step is to really take all these regularization parameters that I have in the game and send them to infinity, okay? So because with that, I want to remove all the regulators and recover the original TBA result. And you can indeed check that this is what happens, so you can do it quickly for the analytic part, for the node data, and when you combine everything together, what you get at the end is precisely the analytic chemical potential that I introduced initially. Okay? So now I was able to show that the thermodynamic scaling limit of the canonical Y-system pertaining to this column transfer matrix is exactly the thermodynamic Bethe Ansatz Y function, which I defined as the ratio of hole and particle density. Okay, so basically we discovered what is the operatorial meaning, exact prescription for this thermodynamic Y function. And not only that, we exactly reconciled the two approaches. So the two approaches are exactly the same. So here is my summary, which is essentially 3 remarks I want to make, and then I'm done. So first of all, keep in mind that in this procedure, unlike in the conventional procedure of transfer matrix, we have never invoked any Trotter-Suzuki-like decomposition for exponents. Instead, what we've done is we use the thermodynamic inversion identity with a combination of a string charge duality, and then we sampled over quasi-particle rapidity densities. So this was our regularization protocol. And not only that, so it turns out that a typical macro state now on this landscape of all GGEs indeed goes beyond this conventional trotterization approach, and this is because of the presence of these null modes. So you will not be able to get that via standard trotterization procedure. You have to use that. So that's one remark. The other is we also never required any numerical analysis on the spectrum of this transfer matrix or any kind of empirical input, since the equivalence between the two approaches can be simply established on what I would say on the interconsistency basis. So you simply have one object, one partition, one vertex model, and you want to compute the partition sum, and you have 2 ways of contracting it. So we just demonstrated that 2 ways give you the same result. Something you would physically, of course, expect, but it's a bit technical calculations to get to this explicitly. And finally, one remark on this infamous string hypothesis, which people often mention as, well, which is often portrayed as the weak spot of the TBA approach. So I mentioned you that the solutions to Bethe Ansatz equation form these Bethe strings, and then we formulated the functional integral approach in the basis of these string solutions. Okay, so, and the question is, maybe something goes wrong, these are not exact solution, maybe there is some more solution, things like that. So with that procedure, we basically show that, no, this solution is basically, they are forced upon you by the underlying fusion algebra, namely the quantized SU2 algebra. So why the two approaches were ultimately reconciled is because we are using the unitary part of the representation theory of this quantum group, and this completely determines the spectrum of both the column transfer matrix and the row transfer matrix, and allows for this unification. So I will conclude with that, and yeah, maybe just mention, so I don't have really conclusions, but it's more like a task, as you know. So my outlook is just the natural next step for this is to try to compute the static correlation functions, which would amount to take some local observables, insert them inside this object, and then again contract. So this is a natural next step. So, which I think is the main practical benefit of this approach. So thank you for
I mean, at the beginning, you talked about the fact that in the long time limit, you will converge to the appropriate GGE.
Yeah, correct.
And now you have all this complicated construction. How far away are you from that goal, actually? I mean, are you actually saying anything about this question, or?
Yeah, so let me go all the way to the beginning quickly. So what I was describing initially was more like a motivation for why these quasi-local charges are important objects. So this story goes back already to 2015 and 16, so where we implemented this program, and we demonstrated that given an initial state, let's say some simple state, it's convenient like nail up, down, you want to quench from this state, and then you ask what is the steady state density matrix.
Are you giving a solution to that problem? I mean,
we already solved it a couple of years ago, so this problem is solved. And yeah, so what is important, what I show you today, it's a explicit regularization of this ensemble, which was not even needed in this procedure. It was enough to basically, well, what I specified here. It's enough to fix the expectation value for local observables. So yeah, so this is a confirmation that the idea of the GGE works for interacting integrable models.
Okay, I'm wondering why you need all this regularization. So what was the reason? So a posteriori, you have to start inventing some regularization.
Yeah, because at the end of the day, you realize that there is really two distinct types of contributions which determine the analytic structure of this landscape. So the part that resides in the null space of this S inverse is the data that remains confined inside the locality strip. The other part is the data that flows towards the boundary. So now still you may ask, okay, why would I care that it flows towards the boundary? This part of the data which flows towards the boundary is the part of that condenses and escapes this canonical contour, which has to be regulated by epsilon. Otherwise, you spoil locality.
The question is,
it explains
after the first regularization with epsilon.
Okay, I probably explained it in a too complicated way. So this goes back to this puzzling question of why certain solutions to quantum quenches correspondent to generalized Gibbs ensembles which violate the thermodynamic, which violate the canonical Y-system relations. Okay, so you find a solution and then say, cool, this solution has to satisfy these functional identities. You try it, it doesn't. Okay, but if you look in the textbook, it should. If you talk to the expert, it should. They will tell you, you did something wrong. It should satisfy it. So here, with this procedure, I demonstrated that there is a distinction between the spectra of discrete models, where you will always have this identity, and thermodynamic models, where part of the analytic data will start to condense, and something bad will happen with it. And this is the origin of this node term, which breaks these identities. Still a bit technical thing. I don't know if I can give you really a good physical intuition for why this term is important, but it's definitely two different types of contributions.
Related to this question, so these quasi-local charges, they form a space and can complete the space, with this infinite summation, and what you get is not quasi-local anymore, numerically. Pseudo-local. So does that correspond to this things accumulating on the boundary?
No, I think throughout the story, the quasi-locality is maintained because my set of charges X is quasi-local, and this presence of positive infinitesimal makes sure that I never touch the strip. So if I never touch it, it means my localization length is always finite, arbitrarily large, but finite, because epsilon is 1 over localization length you can think of. And then this density, mode density operators are just linear combinations of these charges. So they inherit locality. So locality is always maintained. This is another way why it's important to keep this epsilon. Yeah, so.
I have two questions. Probably one question is part of this. After a long time will be given by generalized. Part of this result, do you also prove generalized hypothesis? Right. And a related question, this result, does it of charge psi, those will be given by some infinite number of charges, so smooth distribution.
Right, right, okay.
And if that can be translated to say entanglement of initial physical properties of the initial.
Okay, maybe I try to answer the second question first. So I think what you have to assume is some reasonable condition on the, so some clustering property of your initial state. You cannot give me some Schrödinger cat state which see the whole Hilbert space or something like that. Even if you give me a state like that, I wouldn't be able to compute this average. So, but I think under very mild assumption of clustering, I don't have to assume anything beyond that. And what turns out that, yeah, these functions will be smooth. So I don't know if I can manufacture such an initial state that something bad will happen. I don't think that is possible. No, I will have to think better about it. I never really paid too much attention to this, to be honest, but I think generally you will not have this. No. No, so the thing is already in the idea of this business is that you start with a state which is obviously not a finite linear combination of eigenstates of your model, such that you have really property phasing and the proper thermodynamics. Otherwise, of course, you can always fine-tune an initial state. You will have a persistent oscillation, and then you say, well, it's not thermalizing. So this is something that is always emphasized in every review, essentially, on this topic, that you want to take a. So it means if you express something in a computational basis, let's say, of course, this will not be, will have nothing to do with any eigenstates in the system. So I don't think you can easily achieve anything like that.
But if you take psi to be one highly excited energy eigenstate, then presumably this should be correct. And of course, you don't have to wait any time. Time t equals
Correct.
0.
You are changing the logic now, because you can say, okay, I can already start with a state which is an energy eigenstate, and this is one of these typical states which belongs to one macro state. It's a representative state, and its local content is equivalent to one of these GGEs, indeed. And I can tell you which one, yeah. But I will have to know not only energy,
maybe we can
right,
continue
but also all the
later.
charges of this state. This eigenstate, right? So this you're giving me basically one Bethe eigenstate in the thermodynamic limit, okay? And basically to completely specify that, you will give me the distributions of quasi-particles. And other details I don't really care about, because this is the only part that determines the local correlators. So to also answer your first question, yeah, this has been shown. So the local correlators in a GGE are only functionals of the densities of quasi-particles, but not of individual realizations of these densities. So it means there is always, for every macro state, so observables are functions of macro state, and for every macro state you can find exponentially many eigenstates in the spectrum which have the same values of these local observables. This can be demonstrated because you have all these mappings are explicit. So it's not even a hypothesis. It's wrong to call it a hypothesis. It's true. Simply true.
I think we're out of time, so maybe we continue. So let's thank Enej for talk.